Hi, I'm Ms. Hearn. Let's get started. In part 3 of this series on how to construct power series for particular functions, we're going to look at how to use a known power series to construct other power series. So, for example, if we know that the function f of x equals 1 over 1 plus x can be written as the series n equals 0 to infinity, negative 1 to the n, x to the n on a particular interval, we can determine a power series centered for 0 for a different function based on that. So the function we're going to look at is h of x equals negative 2 over x squared minus 1. And what we're going to do is to use partial fractions to break this guy apart. And we're going to hope that when we do that, we get something like 1 plus 1 over x. So here we go. The denominator factors into x plus 1, x minus 1, so we know we can break this apart into a over x minus 1 plus b over x plus 1. So we're going to write our characteristic equation multiplying on both sides by x squared minus 1. We have negative 2 would be a times x plus 1 plus b times x minus 1. If x were equal to negative 1, that would mean we'd cancel out the a term. We'd have negative 2 equals negative 2b, and we would get that b is equal to 1. And if x is equal to 1, we would get negative 2 equals 2a, which would mean that a is equal to negative 1. So we have that this is actually equal to negative 1 over x minus 1 plus 1 over x plus 1. Now I want to write it so that it looks like 1 over 1 plus x. Now this part is equivalent, so let's just write it that way, 1 over 1 plus x. This part over here, let's put the negative in the bottom there, so we're going to have 1 over 1 minus x. So this is the function f but with negative x plugged in. So here we have f of negative x, and here we have the function f of x. And so writing it as a power series, we're going to plug in the negative x here. We're going to have the series n equals 0 to infinity, negative 1 to the n, negative x to the n, plus the series n equals 0 to infinity, negative 1 to the n, x to the n. Over here the negative 1s are going to cancel out, so we're just going to have the sum, let me write it over here, the sum n equals 0 to infinity of x to the n plus the alternating sum n equals 0 to infinity, negative 1 to the n, x to the n. Okay, let's figure out the interval of convergence. We need to limit ourselves or restrict ourselves to the intersection of the intervals of convergence of the two component functions, if you want to call them that. So here, this matches a over 1 minus r, the sum of the geometric series, if we have r be the x. So that means that in order for that to converge, the absolute value of x has to be less than 1. So we have an interval convergence of negative 1 to 1. And that was for the first part. Similarly, this is matching a over 1 minus r if x happens to be, if r happens to be negative x, because that's 1 over 1 minus negative x. That would mean the absolute value of negative x needs to be less than 1 for convergence, and that's still going to happen on negative 1 to 1. So the intersection of negative 1 to 1 with negative 1 to 1 means that we still have an interval of convergence of negative 1 to 1. Oh, but I do need to write this as one power series. So what we're going to do is we're going to add these two together, adding their coefficient. The coefficient of x to the n is going to be 1. Coefficient of this guy is negative 1 to the n. So we have 1 plus negative 1 to the n times x to the n. And in part 2 of this video series, we saw that that is actually equal to, if you write out the terms, you're going to see that every other term cancels out. So we're going to end up with the sum n equals 0 to infinity of 2x to the 2n. All right, next we're going to use the fact that 1 over x can be written as the series n equals 0 to infinity, negative 1 to the n, x minus 1 to the n, to find a power series for f of x equals natural log of x. All right, so what's the relationship between the natural log of x and 1 over x? Well, we know that one is the derivative of the other, or another way of saying it is that the natural log is the antiderivative of 1 over x. So notice that the natural log of x is equal to the antiderivative of 1 over x dx. And so what we're going to do is use the integration rule for power series. So what does the integration rule for power series say? Basically what it says is that we can apply the power rule for integration. So if f of x is the sum a sub n times x minus c to the n, then the antiderivative of f is going to be c plus the sum n equals 0 to infinity of x minus c to the n plus 1 over n plus 1. So we just added 1 to the power and divided by it. So in our case, we're looking for the antiderivative of our 1 over x, which we know is the series negative 1 to the n, x minus 1 to the n. Oops, I forgot my a sub n here. So we're going to have the negative 1 to the n is our a sub n part, and then we're going to add 1 to the power of x minus 1 and divide by it. So that means that the natural log of x is equal to capital C plus, we're going to have the sum n equals 0 to infinity of the negative 1 to the n stays the same, and then we're going to have x minus 1 to the n plus 1 over n plus 1. So we would like to know what c is, and if we let, for example, x, check what c is when x is 1. So the natural log of 1 would have to be equal to c plus the sum n equals 0 to infinity of negative 1 to the n times 1 minus 1 to the n plus 1 over n plus 1. But this is just going to be n equals, let's write it out. When n is 0, we're going to get 1 times 0. When n is 1, so that's 0. When n is 1, we're going to get 1 times 0, or negative 1 times 0, which is also 0. So we're just going to get a sequence of zeros here. So a sum of all these zeros is just going to be 0. The natural log of 1 is also 0, so we get 0 equals c. So that means that the natural log of x can be written as the series n equals 0 to infinity, negative 1 to the n, x minus 1 to the n plus 1 over n plus 1. If you want to find the interval of convergence, then you would have to use your ratio tests or geometric series tests, and remember to check the endpoints as well. I hope you found this video helpful. If you did, please remember to like it. That helps other students to find the video.